I'm Markus. As you can see, I'm from the Cybersecurity Center of Vienna Technical University. Especially, like in particular, I'm from the Security and Privacy Group. And what I'm going to talk about today is our reachability analysis for WebAssembly called Wappler, and what comes beyond, which is in our case a reachability analysis. All of the things I'm presenting today is joint work with Jeppe Blauberg from Aarhus University, although he's now in private industry, Magdalena Svitro, Alexander Hösten, and my boss, Matteo Maffei. So, I mean, we all know what WebAssembly is here. It's a thing to make stuff go fast in browsers, but you can also do different things with it. For example, you can program cloud infrastructure with it. I'm told some people do that. You can run smart contracts, for example, or as we just heard in two talks ago, you can run plugin infrastructure with it. And all of these things profit from Wasm's very prudent design and the isolation guarantees it gives you. One thing that doesn't work so well in WebAssembly is, for example, stuff like the following thing. When you have a program that's compiled from, say, C, like any memory unsafe language, you would have problems like this. So imagine you have this static constant car, like a string that's called trusted and contains actually trusted as like a placeholder. Then you have like some game state, and from the 6 fields, we know that we are playing like some game that's played on an 8x8 grid, like let's say, I don't know, chess or checkers or something like that. And we have like some privileged external function called eval. So we might want to have a function called update game state, which takes x and y and z, and then just checks, okay, if x is smaller than 8 and y is smaller than 8, we compute like some joint index and set this thing to c, and then we evaluate trusted with using this thing that is assumed to be constant, and we put it into this privilege function. And that unfortunately doesn't work so well. Because these constraints are insufficient, as it turns out, because x and y are signed integers, they might be negative. So if this is then computed, this can overflow, and then trusted can be overwritten. Why is this? Because in WebAssembly, the linear memory is, as all of you know, mutable array, and we cannot enforce any notion of like read-onliness on it. And then we have the problem that we might have set trusted to some untrusted value and passed the stuff to untrusted function. And what is interesting in this regard is that on a modern hardware modern hardware architecture, or like with a modern linker, this code is in a way more memory unsafe on WebAssembly than it is on native, right? Because like in a modern linker or modern MMU can say, okay, this is a read-only page or something like this. That is not our contribution. That is a kind of one of the first impactful WebAssembly papers by Daniel Lehmann et al. But yeah, so how might we want to address this? And since we are doing static analysis, our answer is of course static analysis with so-called safety properties. That doesn't look great.
Markus.
Yes.
Is the trusted thing and game state supposed to be related in some way?
Yes, they are not meant to be related. As I said, in a native environment, they would be on different memory pages. But since they live in the linear memory of WebAssembly, they are kind of automatically related. Like they will be placed right next to each other by executing or whatever. But yeah, obviously they should not be. Like, I mean, a write to game state should not modify anything trusted, right? Good. So safety properties. Safety properties are just properties that can be proven that, sorry, there can be, what's the opposite of proven? Like if you have a counterexample, disproven, yes. Like safety properties can be disproven by having one witness that shows that something is not safe. For example, a safety property would be no integer overflow. And we can demonstrate it by having integer overflow. Having like a program with no integer overflows would help in this case. But there are also situations where you might want to have an integer overflow because like it's well defined in WebAssembly. Actually, it's even well defined in C for unsent integers. We could have something like no sensitive override. We could say, well, trusted lives at a certain position in memory. We don't want ever to call i32.store or like i8.store, i32 store 8 on this position. Or we might have something very overkill in a way. We can say, well, I just asserted trusted contains the string trusted at this position. And all of these are safety properties. So how do we soundly enforce safety properties with reachability analysis? What happens now? Sorry. Yeah, with reachability analysis. And how do we do sound reachability analysis? We make it correspond to the official WebAssembly semantics. This is one of the great things about WebAssembly, is that it comes with a formal specified semantics. We had this already today at many times. Yeah, just to go over it again, we have a store, we have like a frame object that tells us something about functions, function we're in, and we have this heterogeneous stack that contains values, like as you would expect from a stack-based language, but it also contains this control flow, administrative instructions, and it also contains the code to be executed in a way. So how does WebAssembly work? Like how is progress specified in semantics? We vector this instruction list into an evaluation context that looks, for example, like this. Then we look in the WebAssembly semantics if we have like a rule that works with a evaluation context that is shaped like this. We do it, okay, we say, well, we will rewrite this to this, and then, yeah, we go from this configuration to this configuration. So, as we got today already, that's the problem, that is slow. If we directly implement it as specified by the specification. As we heard already today in a talk, Conrad et al. Have a paper on it where they had like to deal with a similar problem for the kind of reference interpreter. So how did we solve the problem? I would argue less elegantly than these other two approaches, but we will see this soon. The way we formulated our analysis is as a Hong clause-based abstraction. A Hong clause-based abstraction works by translating your concrete machine state into a set of first-order predicates. So, for example, here we would have like a predicate M state that kind of models the machine state. We might have a separate predicate for the table, for the function pointers, and so on. And then we have to, for every rule that might appear in the WebAssembly module, we have to over-approximate its behavior by having a Hong clause like this, and over-approximating in order to remain sound. So what were the problems here? Well, exactly this factorization. So how we solved this was we basically annotated the semantics with like function IDs on the frames and program counters on the instructions. Then, well, we introduced these things into our abstraction, and we did some slight modification of the step function, basically to rule out instructions that rewrite to other instructions. Like, for example, the way branch if is defined is by rewriting into branch, and this this branch instruction that is rewritten to doesn't have a program counter by itself in a way. So yeah, that's how we dealt with it rather bluntly. Yes. How does our implementation work? Basically, we have like our own specification language called Horst. And if you look behind all of the ugly type annotations, you will see here that this is just it looks very much like it is specified, like binary operation is specified by taking the first two things from the stack and running a binary operation on that. So with this, we can approximate the semantics of WebAssembly in a probably low 4-digit number of lines that have a close definitional correspondence to the actual semantics. Good. So another point that also was already a topic today was the implementation with embedders. If we consult the semantics for that, well, okay, you know this already. The control flow lives somewhere in WebAssembly. We call out into the host environment, say JavaScript. We return back maybe. Actually, we might already re-enter into WebAssembly, but that's something we won't discuss today. And yeah, that's what the standard says about this, which basically says, okay, you take a bunch of values from the stack, you encounter the invoke function, and you will rewrite this to a result with modified store, although the store modifications are restricted. So you can modify globals, you can modify the memory, you can also grow the memory, and you can modify, well, not modify, but add functions. And you can also, that's the point there, you can add functions and modify the table, which actually means that if you do a sound analysis, a sound static analysis, that every time after you have a call out and you don't know anything about the call out, every call indirect which comes afterwards will do anything with your like semantic wise, because the call out might have added a new function to the store and changed the table to point to it. So we in this work also talked a little bit about how you might like we had a little section on specifying how like the capabilities of basically or the contracts that the embedder provides. Yeah. So the evaluation was rather straightforward. We basically just let it run on on the WebAssembly test suite. Is the required state reachable? Like these are all quite small programs. Yes, we were able to show that the correct state is reachable in 98% of the cases. In 2% of the cases, we timed out within 10 seconds because these were kind of complicated test cases, and we, yeah, where our encoding wasn't efficient enough. Are any other states reachable in the sense of are we precise? Like here, we don't want to have any red part of the thing because we want to have a sound analysis. So this would be kind of an empirical refutation of our soundness. Here, the thing is that if other states are reachable, we happen to be imprecise, but at least we are still sound. Like safety analysis, that is, sorry for us, safety properties, that's good enough. Yeah, and this here, that like we have like the favorable result in 88% of the cases, although this excludes floating point numbers, which we currently over approximate because, and many of the tests are actually concerned with floating point numbers. Oh, something that I might have, I should have said in the beginning, all of this is WebAssembly 1.0. Okay, good. And then we have two small case studies. One of them you already saw with the game example. Good. That's the wrapper for Wappler. It's the first sound reachability analysis for WebAssembly. Well, at least the first we know of. Many possible improvements. Currently, we treat code imported from other WebAssembly modules as host functions, basically. They also, we don't support floating point numbers. Our memory handling is sound, but kind of imprecise. Sorry, not imprecise, but it's too precise in a way. Well, it's stupid. For example, if we have code that is compiled with mscripten, where they try to kind of rebuild the C stack in the linear memory, this kills the analysis quite badly, although these things could be recovered by using like some smarter pre-analysis, which was not the thing in this paper. Well, exactly, we could have analysis specific abstractions, and what's also would be important is that if we would have something like increased composability, because obviously if you just throw a whole module into an automated solver without any annotations or anything, your success chances are rather slim. Okay, but that's just the part that, I mean, this was first presented at CSF last summer. What comes now is current ongoing work, or like actually the work is not ongoing anymore. I hope I will get the accept notification on Monday. Let's cross the fingers. Which is, we took a step back in a way and thought, what is the common patterns of all these application domains for WebAssembly? And it turns out it is information flow. Like all of these things are about managing how information is passed between things and also restricting it. In the cloud environment, we would not know, we wouldn't want to have like different customers interfering with each other in a smart contract environment, the same in a plugin environment, exactly the same. So what we thought about was the OG information flow properties, in a way, non-interference. What is non-interference? Imagine you have a system. The system has inputs and outputs. And what you might be interested in your system is like the secrecy of the information that comes in. So input information might be public or it might be secret. But you don't want to have the secret inputs interfering with the public outputs. Or maybe you are not interested in confidentiality, but in integrity. Okay, so we might have trusted inputs, you might have untrusted inputs, and you don't want to have the untrusted inputs interfering with the trusted outputs of a system. Yeah, you can build a security lattice where basically the most well-behaved information is public and trusted one, and the least well-behaved information would be the secret one that's at the same time untrusted. And you can kind of describe the capabilities of an attacker on such a lattice. And these lattices can be arbitrarily complex if you think about different things that an attacker might want to know or might want to influence. Yeah, that's the formal definition. Basically, inputs, like if the inputs of a certain level are the same, the outputs of a certain level should be also the same. Good. If we revisit our example again, then this could be formulated also as an integrity property on exactly trusted. So basically, we have all of these inputs that are untrusted. Can we modify the trusted thing? Proving that is kind of easy. What's more difficult is proving that a fixed version is actually safe. For this, we need an abstraction that can reason about the memory on a value, that can segment the memory in different regions, and we need to reason about values. And if you know about the literature on information flow, for example, a thing that is kind of popular still are type systems. And then you would have like a type system that would say, well, if you have untrusted inputs, the control flow at write to trusted, so high trust memory region might not be executed. But this would be if the memory region is like the whole linear memory in a WebAssembly module would not be precise enough. In honor of our hosts, here's the second example. Imagine you have like it's a programmable programmable cloud infrastructure. You just get a message struct which has like a secret session and a public payload. And you have two functions. One is called sanitize, which just sets the session to 0, and has session, which just checks if the session is 0. And then you might want to write this code here. We have authorize and execute. Authorize and execute is trusted to handle secrets because we wrote the code ourselves, let's say. It just takes the message, looks if the session ID has some utilities attached to it or something like this, and then runs whatever the payload tells it to do. Then we have untrusted log, which might be a third-party component. And the idea is that both of these functions have access to the whole memory, but we don't trust untrusted logs. So at the time when untrusted log is executed, we don't want to have any secrets in the memory anymore. And then we have a small little, then we have a flag to improve developer productivity, which is called isprod, which just tells you if you are on a testing instance or not. And the process then works the following. It checks if you have a session, that is if the session is on 0, or you are not on a production instance, which says basically, okay, in a testing instance, we don't need to be authorized. Then if this is the case, you run authorize and execute, then you run sanitize, which sets all the secrets to 0, so they're not a secret anymore because they're already 0. And then you call untrusted log. And this might look simple, but most non-interference checkers will not be able to handle this code because, okay, imagine you have a type system, then sanitize, which sets the thing to 0, is executed in a position that is depending on untrusted information or on secret information. So potentially this is also secret. If we have taint tracking, which just like taints all the values, well, good, the values are tainted and they will be still tainted at untrusted log. So what we did is we kind of combined taint tracking with an abstract interpretation, which is kind of value sensitive. So if you go, this is just a compilation of the code. I'm rather late already, right?
We have a longer break, so we can do like.
Okay, I will trust me that this is the code, or a code with the same thing. So yes, exactly. Our approach is called vanilla, the WebAssembly non-interference layer label analysis. Yes, and it lifts, and that's the theoretical contribution of it. It lifts arbitrary reachability analysis to non-interference. That's quite cool, and supports arbitrary security policies like the lattice that we just saw. And yeah, the way it works is by combining abstract information and abstract interpretation and taint tracking. So if we go back to our example, let's say we have like the session, the payload, the stack of WebAssembly, and the isprod thingy, which is stored in a global, like this. Then at the beginning, we taint session because that's the secret thing. Then we go through the execution and call has session, and has session just propagates the taint, which yeah, will either leave us with a tainted 0 on the stack or some tainted non-zero yeah, on the stack. And depending on the session as it was stored, then if we execute left, we will have a tainted 1 on the stack. If we execute right, we'll have a tainted 0 on the stack again. And then we might do a jump, depending on that. And since this jump dependent on high information, we want to taint this whole region. So if any write happens here, we also taint everything that happens here. For example, if we use global get isprod, the result will be actually also tainted. And then we have like two different things. Again, depending on the result of isprod, or like of the local get, global get. Yeah. And And now something interesting happens, which is kind of specific to WebAssembly, is that this thing that we tainted already will become extended, because now this, due to this jump, which executes nothing, which doesn't execute these things become again potential points where implicit flow can happen. Anyway, we continue our execution, and then we end up at the point where our where we have like 3 tainted zeros on the spot, and since we're building kind of a fixed point of all reachable states with taints, we look at all the states, we determine, hey, at this point everyone is 0. If everyone is the same thing, we have a special rule to remove the taint. Voila, we have proven this non-interferent. Great. Yes, the evaluation, we wrote our own synthetic benchmark. We compared with a general hyperproperty solver. We identified some bad randomness in smart contracts. Yeah, we use different solvers for our Hall clauses. Like some things are better with step 3, which has high precision, but is obviously kind of slow. If we kind of interpret our Hall clauses again abstractly, we can get like also real programs analyzed, which we did with this smart contract thing. Yeah, W wrap up. Vanilla is the first fully static sound non-interference analysis approach for WebAssembly. Talk to me if you're interested in academic or industrial collaborations. You might have an excuse to go to Vienna, which is probably the only city in the world that is at the same time voted for the most livable and the most unfriendly city in the world. So, yes, and here again is the thing if you want to. Thank you very much. Sorry for going over.